All right, so this is a lecture for Wednesday's class, October 11th. This is a virtual lecture. You're required to watch this before midnight on Friday. All right, so we're going to go into chapter 8, which is mechanical failure. So we've talked about crystal structures, the defects that we see in crystals, and how those defects can lead to failures. So we're going to start with talking about cracks and voids that exhibit through creating new materials and how those can propagate to cause failure. We're also going to talk about how we quantify the fracture resistance of materials and how to actually estimate when things can fracture. And then we'll go into how things can be loaded if we put a stress or force on something over and over again repeatedly. That can cause these cracks and voids to propagate, and once that happens, the material will eventually fail. This could happen at much lower stresses than maybe if you tested the original material in an Instron machine. If you cyclically load it over time, it can fail at much lower stresses. All right, so this is some examples of issues that we see in everyday materials. The first one here was quite common back in World War II. These were the Liberty ships from the British. They used a type of metal that was tested to have very tough properties when used out in the ocean. But one morning, they woke up and saw that some of their ships had actually split in half right in the dock. They weren't even out in the ocean. And this occurred because the metals actually went through a transition, and it happened to occur at a much lower temperature. The engineers that created these boats didn't think to test lower temperatures, close to freezing of the water. They had tested it all at kind of room temperature values. And what happened was the crystal structure actually shifted because of the change in temperature. The reduction caused the atoms to shift to a different crystal structure, and that structure was much less strong. And just the weight of the boat and then the waves hitting the boat cyclically caused it to split in half. This is the same reason why the Titanic sunk back in 1912. It was made of a very strong, newer version of steel, an iron-based steel, but it hadn't been tested at cold temperatures. And so when the Titanic went on its maiden voyage up into the North Atlantic, where it was basically below freezing with the salt in the water, the water was still liquid, but it was below freezing in temperature. It made the metal quite brittle. So when it hit the iceberg and tore open part of the ship, it should have just tilted and the front of the ship should have filled with water, but they should have been able to continue moving the ship. But just the weight of the ship coming out of the ocean was enough to split the weakened metal because it's transitioned to a different crystal structure. So it split in half and sunk to the bottom of the ocean. Another example would be another temperature issue that we see. This is a semiconductor for a typical microprocessor, and these tiny leads that connect your transistor to the different wiring mechanisms. The heating and cooling from turning off and on your computer, as well as the fan kicking on it and back off again to keep your computer at a typical temperature. That can cyclically load the wires until these small thin wires actually snap. So they change crystal structure at higher temperature. They go back to a lower crystal structure. They keep doing that over and over again. Eventually, the material snaps. And the last one is kind of in my area of expertise. This is a hip implant. It's actually a titanium rod that is being placed into the femur in your leg to replace the hip joint. And then there's a socket component right here that goes into your hip, and then the two pieces come together to replace movement. So this could be done from athletic issues with athletics, or as you higher up in age, you start losing cartilage, and this joint begins to fail. So the problem with this is that there's actually been a fracture. So this is the top of the femur here. It's supposed to be perpendicular to the neck here, and it's actually cracked and shifted to the side. And why is the stresses so high at the neck? Well, we know this from our material testing lecture. This is the smallest area, cross-sectional area. The force being applied by the body is going to be the same throughout the material. Divided by the smaller area, you have a higher stress at the neck. And just from the loading over and over again, there are probably some voids maybe in the material that compromise the surface, the cross-sectional area, and cause the material to fail prematurely. Okay, so what are the types of fractures that we see? So we have ductile and brittle fractures. So ductiles we've talked about, basically ductility is plastic deformation that's permanent, whereas brittle fracture has little or no plastic deformation, but then the material just breaks. And the difference between these two is ductile fracture is predictable because we see the deformation occurring. We can watch it, and in most cases we use that to say, okay, we need to replace this part before it fractures completely. It's predictable and we know that we can fix it. Brittle fracture, we're loading the material, something like maybe like a ceramic. We just see no deformations in the material, and all of a sudden the sample just fractures, basically explodes. This is what we would call unpredictable. And the fracture is considered a catastrophic because we can't estimate when it's going to happen, and when it does happen, it's usually very dramatic. And if it's an engineered material, it could cause fatalities. So we typically want to see predictable fracture mechanisms because we can see them before and address them before they occur, whereas brittle, we have no warning, and the material can fail typically catastrophically at any time. Okay, so we have to keep that in mind when we design devices. All right, so how does this look if we actually took a material and placed it in an instrument machine and ripped it apart? So the first one we'll see, we had a material that was a rod of known diameter. We pull on it, it stretches, this surface area gets smaller and smaller, the cross-sectional area gets smaller and smaller until it separates. So large deformation, very predictable, large ductility. In the middle one here we have similar material. We see it does reduce in area, so it is visible. And we get this kind of tearing effect where it tears apart and splits and then lets go. This is more of a moderate ductility. We don't get as much stretch from it, but we still see the variation. Then the last one, material has a similar cross-sectional area. We fatigue it, we add force to it, we add stress to it, nothing seems to happen. All of a sudden it splits in half. No warning, no deformation that we see. So thinking of these three, these also follow the three types of materials that we've talked about in this class. We have metals, we have ceramics, we have polymers. So which one of these is each material? Which one has a lot of stretch, a lot of ductility, a big change in cross-sectional area? This would be a polymer. More of a moderate change in cross-sectional area and kind of a ripping of the material until it separates at the edges, pulls apart. This would be a metal. And then the last one with no change in cross-sectional area, sudden fracture, no warning. This would be a ceramic type material. Okay. All right, so which one do you want? If you have a pipe filled with a toxic gas, you're working at a refinery or some other system, and you're the one that has to go around and make sure everything's working, all the pipes are running, all the valves are open. So if you're walking by for your inspection one day and you take a look at the pipe and you see a bulge starting to form in the side of the pipe, that gives you an indication, oh, okay, I can turn this pipe off, I can report it, maybe we can come in here, take this piece out, replace it with a new piece, and then turn it back on. No fatalities, no other issues. Or maybe you're walking along and you have an older type pipe system and it fractures, and it fractures catastrophically, very brittle. There's no bulge that shows up first, it just explodes. If you happen to be walking by and a material explodes on you, you're going to get toxic gas, or maybe the shards from the pipe are going to fly through like a claymore mine and go right through your body. That would be bad, right? So the idea is we want predictability. This is not predictable. It can explode at any time, and when it does, it'll be catastrophic. If there's anybody nearby, you're going to have fatalities. Whereas this one, you get warning, you see a deformation, and even if it does split, you have a much lower chance that maybe it split in a certain direction. It might be straight up, where it wouldn't affect the person walking by. I mean, there is a chance that it would go in the direction that people are walking, but there's a much lower risk of fatality from this system, and there's the predictability. You see a lot of deformation before it fails, which gives you the opportunity to fix it. All right, so these are the types of failures that we see. Two types here. So we basically have the brittle fracture over here and the moderate fracture at this side. So this would be an aluminum material here. You can see the fracture is called a cup and a cone fracture. You see it kind of dips in as a cup here. The cone shape is on this side. So when you're pulling apart, the cross-sectional area starts to change, and then it starts to tear at the weakest point. It usually starts to tear from the inside first. You get these little bubbles where it tears away from the material. And then the edges are the last to go. That's the last part holding the two materials together. And then it tears at these 2 points. So this is a typical moderate ductile failure that you would see in metals. This is a very hardened metal, and it has a more of a ceramic type failure to it. And you will see that there's constant surface area here, constant surface area, and then it seems to just break. No warning, no change in shape or area. And if we look closer, there's a reason why this failed. If you look right here in the front, there's a little void, some kind of dimple in the side of this piston. And this is where the stresses were concentrated and where the material failed. So why do you think it failed at that point? Well, one reason would be the void takes up no cross-sectional area, so it's actually taking away from our cross-sectional area at that point. Our cross-sectional area is a little bit smaller, and therefore the force being transmitted through there, the stress becomes just a little bit higher at that point. So that's really why it picks this place right here to fail, is because the void changes the cross-sectional area. But the main reason too is the shape of the void actually amplifies the stress. So say I have 100 megapascals of stress in this piston. The piston's supposed to handle 150 with no problems. The edges of this void, because of its shape, actually amplifies that stress, and it could be seen 200, 300, 400 megapascals right at the edges, which is well above the 150 that the piston was spec'd for. So it starts to crack and propagate, and it all of a sudden kind of goes through the material and it fails in all directions. Okay, so let's talk a little more about these cracks and voids. Okay. So again, failure stages, we pull on a material. If it's fairly ductile, we'll start to see the necking occur where it's normal size here and then it starts to shape. We start getting these voids that start in the center, called void nucleation. Those will coalesce together to form one big void, and then it'll spread out towards the edges. It'll reach the edges where the material is still being held together, and then it'll fracture. It fractures at the edges. Okay. This is an SEM of the voids. So when you take a SEM, scanning electron microscope, you plate the material in a gold film, and when you do that, these air pockets actually get kind of filled in with the gold material, so they look like metal beads, but they're actually air pockets. So these are those void nucleations that are occurring. These will coalesce together to form one big void, and you can see where it starts to tear apart from the other surface. holds on at the edges, kind of like a crater. Looks like a crater, right? We've got the edges of the crater, the inner part holds on, and then the edges pull, pull, pull until it pulls apart, and you create this kind of cup shape around the outside. So that's the typical failure for metals. That's what we're emphasizing in this class. Okay, so these typically occur because of some kind of void or crack at a point. These can occur quite commonly when we make materials. When we cast them at really high temperatures. So we have a lot of voids just from atomic vacancies that we talked about a couple weeks ago. We also can have other gases and things in there that are impurities that are in the way when we try to cast these materials, and it could leave spaces or voids within or on the edges of our casted material. Okay, so here's an example of two types of cracks, and we're going to define the shape of the crack and its properties so that we can determine what type of stresses we'll see with respect to the crack. So the first one is a void. The void would be on the edge of a surface, and we assume that all these are elliptical shapes. So when it's on the side, the other side of the ellipse is not there, right? Because it's the surface, it's the center to the edge is our distance, kind of our radius. We call that A, and that is the length or half the length of the crack, right? So if it was inside the material, we would have both sides of the void. So our A would be in the center to the side, that would be A. So obviously the diameter all the way across the void would be 2A. So if it's on the surface, it has a radius of A. If it's embedded in the material, it's going to have a diameter of 2A. Okay. So the other way we define it is the curvature. So obviously these are ellipses, so we're just assuming that each one of them has the shape of an ellipse. And we can do this for any crack or any void in any material. So we can have an ellipse that has an A that's pretty small, but it can be a very tall ellipse, right? Or we can have a perfect circle, which has a radius of A as well. Or we can have a long, low-sloped ellipse, kind of like in the picture. Center to the side is A. What's the difference here? The difference is the radius of curvature. Okay, so let me do a different color here. Let's see, why is it? Let's hope it, okay, here we go. Different color. Radius of curvature. So this one, the really tall ellipse on the side here, if we went along the side, if we tried to draw a circle that has that side parallel to the force, so we see they have the force here, the curvature is parallel and the A is always perpendicular, right? So A is measured perpendicular, curvature is measured parallel, okay? So this is the curvature parallel to the force. The radius of curvature would be what would be the radius that it would take to draw a perfect circle that has the edge of this crack. Okay, so this would be my rho sub t. In this case, my rho sub t is much greater than my A, because the A is really small. The width of the crack is small, but its height is really large, so my rho sub t is really large. Okay. In this case, I have a circle. It has a radius of A. The radius of curvature would also be A, right? Because to draw a perfect circle over a perfect circle, I would need to start from the same center. My rho sub t and my A are the same, so A equals rho sub t. So that's the second type. So this is the first type, this is the second type. In the third type, we have a large A, but if we look at the curvature of the side, I'll just do this side so it's less messy. I would only have to go in a small distance to create a circle of that curvature. So I have a small rho sub t. So my rho sub t is much, much smaller than my A. Okay, so those are the three scenarios that we can have. And this equation here helps us determine what kind of stresses we're going to get with the three scenarios. So the relationship is the localized stress, which is the stress that we see right at the edges, of these cracks, where basically the stress parallel to the stress that's being applied, which is sigma naught. We're comparing those two. Okay. So the first one, my rho sub t is much, much larger than A. The equation says that my localized stress, or sigma m, is 2 times the stress being applied times the square root of the radius over the radius of curvature. Okay. So let's look at what these would be. So in this case, rho sub t is much greater than A. If we put that into the equation here, we're going to get a very small fraction, right? We have a small a, a large rho. This number is going to be very small. We multiply it by 2, we're going to get very low stresses. So these kind of cracks or voids that stretch out parallel to the stress are actually not stress concentrators. They have very low localized stress, and they don't propagate to cause a material to fail. Okay. Whereas a center material equal A and equal rho sub t, perfect circle. If I put that into the equation, A and rho sub t, this is going to be 1. Take the square root of 1, it's still 1. This basically says that for a perfect circle, my localized stress is twice the stress seen that's actually being applied to the material. Okay. So we automatically have double the stress. Okay. And then the last one, this is the most dangerous crack. It has the most potential to cause failure. It's because the rho sub t is very small, the A is very large. If I plug that into my equation, I get a very large fraction. Take the square root, it's still a big number. I have to multiply that by 2. I can get 2, 10, 100 times the localized stress at the edges here than I would be actually being applied. And this is what a brittle material looks like. It has very high localized stresses. To release that stress, the crack propagates, and it keeps propagating very rapidly. So this would be basically a crack in your windshield. Something like you have a pebble hit the windshield, crack propagates in both directions. They typically will propagate perpendicular to the stress of the window. And so when we're defining that, we're basically drawing the crack as a very shallow ellipse, like this, right? So my rho sub t is tiny, but my A is huge. And that's where I get crack propagation. So when they fix a windshield, obviously the easiest way is to take the whole windshield out and put in a new one, but they can also fill the crack with a clear polymer material to fill in the void. But that's not all they do, right? Because if I just fill in the void with a polymer, I'm not changing the size or shape of the crack, and the crack will just keep growing. So you'll fill it in, it'll be good for a day, and then a couple days later it'll grow even bigger. So what they do is they drill a hole in your windshield at each edge. They drill a perfect circle with a drill bit. So what they're doing is they're taking a sigma m that was much, much greater than sigma naught, and they're turning it into a sigma m that is 2 times sigma naught. So they're reducing the stress dramatically. I mean, it's not going down completely, but they're reducing it, and then they could put in the filler, fill in the holes, and fill in the crack and fix your windshield that way. Okay. Typically they'll do this for a crack that's small, right? When you first hit the windshield, they'll drill the whole crack, and then they'll fill it with the polymer material. And that reduces the stress by substantially, but it's still twice the stress locally than the rest of the windshield, so that could be an issue. So a lot of times just replacing the whole windshield is a better way to go. All right, so this is just an example of how the localized stress gets higher as you get closer to the edge of a crack. And again, the edges are parallel to the stress, sigma naught, but the distance is perpendicular. Right? The distance of the crack is measured perpendicular, and then the radius of curvature is measured parallel to the stress. So this would be the sigma m. And as you see here, as you're further away, you reach sigma naught, but as you get closer to the edges of the crack, you can have a sigma m that is much, much greater than the sigma naught. So let me get over to Top Hat here. Let's see. So let's take a look at a question here. Let's start with a review question. This is from the lecture on Monday. We talked about recrystallization temperatures. So this question asks, recrystallization temperature, or T sub r, is typically less than a third, or 0.3, of the melting temperature, or T sub m. Is that true or false? Okay. So we talked about that you have to hit that temperature, hold it for an hour, and you can reset the crystals. That would be false. The actual temperature was above 0.3, usually between 0.3 and 0.6, or about half of the melting temperature. Less than 0.3 is actually called the tempering temperature, which actually helps relax crystals, but it doesn't reset them. And we'll talk about tempering when we get into phase diagrams for metals. Okay, so that was the first question. Let's do another one. All right, so the next question is related to the crack propagation we were just talking about. A local stress that causes crack propagation in a material increases with what? So how are we going to increase local stress, or sigma m? Increasing the crack length, A, decreasing the crack length, A, or increasing the radius of curvature, rho sub t? Or is it both, increasing crack length and increasing rho sub t? Okay, so hopefully you answered A. Crack length is on the numerator of the equation. Therefore, if I increase that, I increase the localized stress. If I increase rho sub t is in the denominator, and it will counteract increases in length, or A. So that won't help, A and C. And then obviously decreasing length, A, will not. It'll decrease the stress. If you decrease the radius of curvature, which is in the denominator, that would definitely increase. Okay. All right, so with that question, I have a second question I'm going to ask you. This is for extra credit, and if you give me this answer before midnight on Friday, you'll earn some extra credit. And the question is, if the length and the length A and the radius of curvature rho sub t are equal, what is the localized stress? How many times greater is it than the stress being applied, or sigma naught? Okay, so you give me try to determine that answer, and later in this lecture I will tell you how to send me that answer. So you need to follow those directions as I tell you later. All right, so let's go back to the lecture. All right, so this is the idea of the crack propagation. It's more of a realistic look at it, right? So this would be a crack like I was talking about that you see in glass. Very small radius of curvature at the edge, very large A. This is a very brittle material. Ceramics act like this, and glasses, which are a subset of ceramics, versus ductile materials. Ductile materials, you can have the same A, crack that forms, or a void, but the edges will start to blunt out. When the edges blunt out, my rho sub t gets larger, and I get a slight reduction in the localized stress. The larger rho sub t gets, the lower the localized stress. And we see this in metals, and especially in polymers. Okay, so this is really the idea of self-repairing materials. If you've heard of some of the new concretes that are being devised in civil engineering, they are adding polymer materials to the rock and the ceramic components of concrete, and you're going to have natural voids in the concrete when you create the material in the first place. When you pour it, you can have air bubbles in there, going to create voids. But as the concrete is fatigued, like a building is maybe swaying over it, or it's being stressed over and over again, the that stress can be dissipated locally because the polymer will start to stretch out, creating a larger rho sub t in the direction of the stress. The A stays about the same. The voids don't really start to change shape. So as the rho sub t goes bigger, A stays the same, the material's localized stress goes down, down, down. And these are called self-repairing materials. They are blunting out the cracks that already are there, keeping them from causing the material to fail. Okay, so when we build materials, we want to follow these rules. We want, if we have a defect or a void, it has a length of A, we want to increase the curvature parallel on the edges of that void. Okay, so we see that in a lot of braces and brackets that are made for building and for other uses. We have right here, there is a curve on the edge of this material. Obviously the upper part has a much bigger cross-sectional area, so the force that's being applied, the stress is much lower. Stress is going to be a lot higher here. Same force, much smaller area. Where is this material going to want to fail? Typically it's going to want to fail on the smaller area, but it's also going to want to concentrate in the transition between the two materials, right? And if the material has a right angle or a 90-degree angle versus a smooth curved angle, it's going to have a much different result in how it fails. So in this one, essentially this is a small rho sub t, whereas this one has a much larger rho sub t. And then I have a void defect length of A. This one has the same void defect length of A. So in this case, much smaller rho sub t, it would want to crack at this position, but if I blunt out the curve, I reduce the localized stress and I minimize the fracture of the material at that point. Okay. So again, this would be my rho sub t, and then my distance in would be my A. So a lot of times you'll see a K value. This K value is essentially A over rho sub t, take the square root. That is that part of the equation that gives you the value. So it's the relationship of the length of the void and the radius of curvature. Okay. So as we see here, larger K sub t's related to the radius versus the height. So the radius would be the radius of curvature, the height would be the h, would be the change in the shape. And we can reduce that down by increasing the radius of curvature with respect to the length of the curve. So this is really h would be more like the a. It's the length of the void. So 1 to 1 would be perfect circle, whereas if we go inward, our k values go up very quickly, and the k just equals the sigma max over sigma naught. So it's rearranged in the equation from before. If we can reduce k 1 or less, then we can reduce the localized stress. But if we have sharp corners, sharp curves, the k value jumps up very rapidly and we'll have more tendency for failure. Okay, so let's go into impact testing. So we see how a material can be improved so that it doesn't fail under normal loading. But impact is another form of energy transfer that can make very ductile and very tough materials actually look like they're brittle. So impact just means force over a very small time frame. So materials act differently if you pull on something, do it very slowly, and it bends, and then it just kind of stays that way, versus if I hit it really hard with a hammer, you're going to get a different response. Okay. So ductile materials under impact usually become more brittle, so they have more likelihood of breaking or fracturing because of the increased amount of energy very quickly over a short amount of time. The material doesn't have time to deform, so it'll actually act like a brittle material. So impact decreases. If it makes it more brittle, that means it's decreasing ductility, right? They're inversely proportional to each other. So how do we measure that? So typically you'll take a sample of your material, like here. You put a little indentation in it to reduce its cross-sectional area at that point, and then you impact it with an outside force. The stress at that divot here is going to be a lot higher than it would be anywhere else, so we're basically forcing the material to break at the divot. What we do is it's a simple potential energy, kinetic energy calculation. You bring up some kind of hammer system, you lift it to a certain height, which gives you a certain potential energy, you release it, that energy turns into kinetic energy, it hits the sample, breaks through the sample, and then the pendulum swings to the other side. So if you had a very brittle material, brittle materials can't absorb energy. They're not tough, right? That's the definition of toughness, the amount of energy that can be absorbed into a material before it fractures. If it's brittle, there's very minimal absorption of energy. So what happens if you hit a brittle material with this hammer? It's going to swing around and going to go up to almost the same height as you started. That means that all the energy was transferred back from potential to kinetic back to potential again. Very little was absorbed. But if you have a material like a very tough metal, you swing the hammer and it hits, it's going to embed in the material, and if the material can stop that from happening, it'll absorb all the energy and the hammer will stop. So that all the energy was transferred to the material. So obviously it's usually somewhere in between. The material will swing up to some level and we can determine how much energy was absorbed or how tough the material was and how much energy was transferred back into potential energy. Okay. But again, most materials that are very tough to start with become very brittle when you impact them, and that just means that they lose their ductility. Okay, so this is what happened with those boats that I was telling you about before. So impact energy can change with temperature. So we talked about iron in particular has different crystal structures at different temperatures. It's body-centered cubic at room temperature, and then as you heat it up, it becomes face-centered cubic, and then it can change again at a higher temperature. What we've seen here is most FCC metals, copper and nickel in particular, they have a pretty constant impact energy with respect to temperature. So temperature's on the bottom, so this would be cold, this would be hot, just kind of a qualitative example. The energy that's needed to break a material goes down a little bit at cold temperatures, and it goes up a little bit in warmer temperatures. But overall, there's not much of a change. But a lot of BCC metals and many polymers, they undergo a transition, right? At warmer temperatures, they can handle a lot of impact energy, but there's a sudden temperature change where the impact energy drops dramatically. And this is what happened with some of the ships that were built in World War II, and before that with the Titanic back in early 1900s. They used a material that had nice impact energy and strength at room temperature or normal water temperatures, but it wasn't tested at very cold temperatures like 20 degrees Fahrenheit or below 0 degrees Celsius, where the water can still be liquid because of the high salt content. The metal transitioned, became much more brittle, so an impact from energy from a wave or from an iceberg or whatever, just the weight of the ship itself pushing down on it could cause it to fracture. Okay, so it's very important to make sure you understand the entire range, temperatures, environment that your system's going to be in, and you have to test it at all those different ranges to make sure that the material stays consistent throughout the range that it's going to be used in the real world. So again, this is the last half of the Titanic, which is a couple miles away at the bottom of the ocean from the other half, which James Cameron and his large amounts of money and his budget for making movies, he went down and actually found the Titanic. And he determined also that, I think I would have mentioned this before, but in his movie, The Titanic, the ship hits an iceberg, splits open in the front, fills with water. The ship starts to tip, so it comes out of the water at an angle theta. And in the movie, The Titanic, which I'm sure most of you have seen, the angle is extreme, right? Way up like this, huge angle. People are falling off of the ship, and the ship splits in half and goes down. In reality, he actually recalculated this. He worked with engineers. He went down and saw the Titanic. He actually dove down with a submersible. They did the recalculation. It turned out it was only about 10 degrees that the ship tilted, just because even a small 10-degree angle, you could still stand without falling down. But the weight of the ship coming out of the water was so great, and the material was weakened because it was cold, it split the ship in half. So it didn't go up to a 80, 90-degree angle like in the movie, but of course it makes a lot better movie to see the major effect of the ship shifting than it does to see it just move a few degrees and then break in half. So that's kind of where, that's the artistic license that was used in that example. Okay, so there's ways of kind of estimating the toughness of a material. We use that using the stress concentration factor. This is different than the K value for the Griffith-Crack equation, right? We had Griffith-Crack as sigma m equals 2 times sigma naught A over rho sub t, take the square root. This was the KT value. This is a little bit different. This is more of the overall toughness of the material and how we can move within that range by changing the shape of the voids in a material and determining how it can handle those. Okay, so the idea is if we have smaller A's or smaller void sizes, the material can handle higher stresses before it fractures. But if the voids get too large, the material can handle much lower stresses before it fractures. Okay. So the idea is when we're processing a material, making new materials, we want to keep the fracture diameters, or excuse me, the fracture radius, the void length, as small as possible so that we get the highest stresses that the material can handle. And it's a very simple equation. It's related to what we talked about. The overall toughness is related to the material properties. The y is usually, in this class, we're just going to assume it's 1. This is isotropic. So if you had an anisotropic material, you can change this variable and get a more specific toughness, usually with respect to direction. But in most cases, we're going to assume it's isotropic. So the real equation we're going to use is the K LC equals the critical stress that we apply times the square root of pi and the length of our cracks, A max. Okay, so that's the one we're going to use. So let's use this equation and do an example of how we can determine what kind of stresses a material can handle with respect to the largest size of the voids that might occur in the material. All right, so I'm going to switch over to OneNote here and do this example. Let's see here. Get out of this real quick. Keep that, and we'll take a look at OneNote. Okay, this is the problem that we're going to do. All right, so let's put it in a scenario here. So we are given a problem where the toughness, stress concentration factor, or fracture toughness, excuse me, I think I misspoke before. So the K sub t that I told you before comes from the Griffith-Crack. That's called the stress concentration factor. What we're using is KLC, which is the toughness factor, or the fracture toughness. Okay, that's K sub LC. And for this material, it has 26, and we have square root of a distance. So it's actually square root of the megapascals times distance in meters. So that's the units for the fracture toughness. It's the square root of megapascals in meters. So we have a scenario where our maximum void size, so the radius of the voids, is 9 millimeters. And we take this sample, it has these large voids, 9 millimeter voids, we put it in an instrument machine and we check it for its original stress to fracture, and we get that it fractures at 112 megapascals. So the material's toughness is the same no matter what. So that's my KLC. So if it's a steel and I have 9 millimeter voids in it, the overall toughness of the steel is the same. It's the voids that are causing the stress concentrations and the fracturing. So if we can reduce the length of the voids, we can improve the strength of the material. And we use the toughness being the same to estimate that. So we can process this material, and we know that if we work at it, we can get the maximum void length down to 4 millimeters. What is the stress that this same material can handle? Obviously, I've decreased the length of the voids, therefore my stress should go up, because this equation here basically shows us that if I move it over, 1 over the stress equals pi times the length of the material. That's the ratio, and then K is our constant, right? So K is right here. So the stress is inversely proportional to the length of the crack. Okay. So how do we calculate that? We just use this equation. We compare stress A, or let's start with stress B, the unknown, stress B, we'll put that at the top, with respect to stress A, and we relate that to the equation. Okay. So pi is a constant, K is a constant, we can cancel those out. We're just left with square root of inverse, so sigma B equals the crack length of the A component. Sigma A would be the crack length of the B component. So that's the equation that we can use and just plug in our numbers. So sigma B, I'll solve for that. Sigma B equals sigma A times the square root of the larger cracks over the smaller cracks. Put in my numbers. It's 112 megapascals for sigma A. The larger crack is 9 millimeters. The smaller crack is 4 millimeters. Okay. And again, the units are megapascals meters, but I'm comparing, as long as I compare the same units, millimeters to millimeters, I don't have to do any conversions of my calculations. So this narrows down. 112, square root of 9 is 3, square root of 4 is 2. So I'm getting a 150% increase. So sigma B equals 168 megapascals. So like I said, the toughness of the material is the same, because it's the same material, but decreasing the void length from 9 millimeters to 4, we've increased the strength of the material 150%. So a lot of it comes down to how good we can process, how form our final material. If we do it very cheaply, very quickly with large voids, you're going to have much lower stresses that the material can handle. If you do it, put in more time, be more careful with your formatting, you can get the material to increase its strength quite dramatically. Okay. All right, so let's go back to the slides here. All right, so let's talk about fatigue. So fatigue is a cyclical stress that's applied to a material, where you add a stress, you release a lot of that stress, you add it again, release it over and over again. You do that over a cyclical time period. So you have a set time, basically a sinusoidal wave, where you have a maximum stress and a minimum stress, and you apply it over and over again throughout the specimen's lifetime. Okay, so a lot of times we can, if something like your heartbeat, 60 beats a minute, we can, if we have something like a heart valve they want to put in the body, it needs to be able to cycle at 60 beats a minute without breaking, right? One of the things that's nice about these cyclic loading is we can build a machine that will cycle the heart valve at, say, 300 beats a minute. So you would apply the stress, release it over and over again, maybe 5 times, 10 times faster than the heart. And that's a way of testing the heart valve in a shorter period of time, but the same but using the same number of cycles that it might be in a patient for their lifetime. So it might take maybe a couple months to test a heart valve that would last for several years in a patient. So that's what fatigue is useful for, is once you understand the maximum and minimum stresses, you can adjust this time to increase the rate and test materials more rapidly. So what happens when you fatigue a material? Well, what happens with fatigue is you have a yield strength that's known. You take a sample, you put it in an instrument machine, you tear it apart, you get a yield strength. Fatigue says that the actual stress that the material sees every day can be much lower than the yield strength, but eventually the material can fail at that lower stress. And why is that? Well, it's important to understand because this happens to about 90% of all the materials that we build every day. They fatigue and break at much lower stresses than they were built to handle. So why is this happening? Well, basically what it is it's the crack propagation that we talked about. We have voids or natural cracks in the material when we make it. When we fatigue it, we release the stress and do it. That energy is transmitted to the cracks. The cracks release that energy by getting a little bit bigger, so their A gets bigger. Their erosive T usually does not. So they start to propagate, and they keep doing that over and over again as they're cycled. The cracks will propagate until the material fails. But this can happen again because the localized stress is very high, even though the overall stress being applied can be very low. As long as that localized stress is higher than the stress of the material, the yield stress of the material will eventually fail. Okay? So the overall stress we're applying is much lower than the yield stress, and that can cause failure. So this is really what we see with samples as we test multiple samples over a long cycle time. And we'll see that some will fail. Say this one fails, starts to lose its stress here. Another sample of the same type loses it at a lower value. This is the uncertainty that we see in samples, right? Because we create two exact samples, but we may have different size pores or voids in those just from how we processed it. So we're going to get variation in the samples. So we typically will test many samples and get kind of an average, and we'll get kind of a standard deviation, right? The material should fatigue down to this level, but it could last as high as this or as low as this. So that's a standard deviation I talked about in the last virtual lecture. So this is what we typically see. There's some interesting differences here. One is aluminum, right? So we'll kind of extrapolate this out. Say we have this aluminum, it's been strengthened. So when we put it in the Instron machine, basically close to 0 cycles, we test the Instron, we get a yield strength, we'll call this sigma ys for yield strength. We get a yield strength of about 52 for the aluminum. So this is a strength of aluminum. The steel was around 60, so it's a pretty strong aluminum. It's been alloyed so that it's almost as strong as steel. There's a problem though. If we fatigue it, so we cycle it, we apply a stress over and over again, the aluminum will start to lose its yield strength. So now its yield strength is actually going down. And as we cycle it more and more times, the yield stress can drop low until it finally breaks. Okay, so the breaking point would be over here somewhere. This material breaks at 15, which is almost 4 times lower than its original strength. So over time, the cracks propagate in the material, the voids get bigger, surface area gets smaller, and the material will fracture. But we have other materials, like we mentioned, if the edges of the material, the sides of the cracks can blunt out, or the radius of curvature can get larger, we can actually stop the propagation. And we see that a lot of times in steel. Steel does lose its yield strength, but then it reaches a point where all of the cracks get blunted out and the stress is no longer higher, and it reaches a limit. Okay? And this is really useful because if we engineer, say, the material to never go above a stress of 25, as we cycle it, the steel will lose stress, yield strength, but it will stop at about 30. And in this case, this amount of stress being applied to the steel would never break it. However, if we go the cheaper route and use aluminum instead, this material will break right about 1,000,000 cycles, 10 to the 6th, right? So steel will continue to last, whereas the aluminum will break after 1,000,000 cycles. Okay? Even though they had very similar strengths to start with, picking the right material is very important. This fact that steel in particular has an endurance limit where it stops losing its yield strength is a really unique property. Okay? So the idea here is there's a safety factor, right? We test this material. We know that its initial yield strength is up here. As long as we don't stress the material above this safe line here, where the endurance limit starts, if we work in this area, then we're guaranteed that the material will not fail. Okay, and that's called a fatigue limit. Whereas that length does not exist on things like aluminum because the cracks do not blunt out. So even if we're staying in that same safe area, once this stress crosses this line, the material will fail. Okay, so we can avoid that using the right type of material for the right job. Okay, so this is the equation that's typically used to determine the propagation of the cracks as they grow. Okay, so we're just going to go over, this is more kind of a visual type thing. We're not going to go into a lot of calculations on this. We just want to understand the equation. So the change in the length of the crack and the change in the number of cycles. So as we cycle the material, the length of the crack will increase. And this increases by the K value, the toughness value, to some factor, right? So essentially, stress changes with the crack length. So we can use this to estimate at different values, and we can use this to determine how it changes as we cycle it through multiple fatigue cycles. So the idea is the cracks grew even though the critical K value, the K that we calculate here, is smaller. Excuse me. So what we see is if we increase the change in the stress, so that's our cyclic fatigue, we'll get an increase in the crack length growth. And as we increase the frequency, so this is the amplitude basically of the stress, we'll increase the length of the cracks. And also, if we increase the loading frequency, which means we speed it up, maybe several hundred samples or cycles a second, or several hundred cycles an hour, versus maybe a few cycles an hour, if we increase that, we also see an increase in the length of the crack growth. All right, so I have a question here, so let's do a top hat question. Get that loaded. Let's see, let me exit out of here. Gotta find a better way to exit keep. All right, let me switch over to questions. I believe it's question 18. All right, so we have, due to fatigue, a material can eventually fail even if the cycle stress is below the yield stress of a material. Is this true or false? So basically a material typically doesn't fail until its yield stress, but if you fatigue a material with a lower stress than the yield stress, you will eventually cause it to fail. Okay. There are some materials that have an endurance limit, but their yield stress still drops dramatically. So if I did increase the stress I applied into that range, I would still destroy the the steel, but if I stay under that endurance limit, the material would not fail. So, but the fatigue is defined as a lower stress than the yield stress can cause a material to fail once it's cycled enough times. Okay, so let's go back to here. All right, so that gets us to creep. So creep is kind of the a variation of fatigue. So fatigue, you cycle a force over and over, you apply it, then you release it, you apply it, then you release it over a set amount of time. Creep, your force is constant, so you stress the material constantly, and the material eventually starts to relax. Okay, so the material accommodates to the force, and so I'm bending the material, it's staying, it's supposed to be in its elastic range, so if I let it go, it should bounce back, but if I hold it long enough, the material will start to relax, and then when I release it, maybe several hours later or days later, the material may not go back. And that is basically dissipating the stress that's inside of the material by relaxing the atoms, and that's called creep. Okay, we see that we have primary, we have three components to the creep. We have a primary where the material, the strain goes up kind of dramatically with respect to time, so we see kind of a instantaneous response, a nonlinear response to the stress being applied. And then it gets to the secondary where it becomes steady state. Steady state means that the creep or the deformation, the change in shape of the material over time is constant. So that means it has a constant what? I'll draw it on here. And that's the second question for the for your to get some extra credit. If you can give me the answer to the first question, as well as what this constant value would be here, what's that called when you take the that curve of the straight line and you calculate its this component here. If you tell me what that is in an email, the email must have a subject line, lecture 12, and in the body you must put the answer to the first question, and then on the next line put the answer to this question. What is the definition of this? Okay. If you put that in an email and send it to me before Friday before midnight, I'll give you some extra credit. All right, so we have a constant range there, and this is where we like to model creep. We model it in this secondary creep region because everything is constant, right? It's easy to calculate. Then at the end, right before it breaks, we get another jump where the strain increases, the time decreases, and the material finally fails, right? So this nonlinear region on both ends is hard to predict, but the majority of the material goes through this constant range, and that's where we do our predictions. Okay. All right. So in the secondary creep, this is where we estimate failure of a material because it's constant and we can predict when it's going to fail. All right. So how do we do that? Well, it follows the same rule we've seen so far. We have a constant energy, kind of a toughness of a material that's known for the material. That's our K value. We have the strain, which is the rate it's deforming over time. And we have our exponential equation. We have our initial stress. We have an activation energy for creep, so it's the resistance of the material to creep. We have our gas constant and our temperature. Same exact equation we use for diffusion, same exact equation we use for vacancies and atom crystals. This also helps us determine the strain rate. Okay? So the secondary is a constant slope region, which if you're listening, that would be the answer to the second question I gave you. So put that in the email, like I said. And then you take the natural log of each side, and you can have a constant, a sloped line that you can estimate. Okay. So what do we see? What does this mean? Again, we say it's the reciprocal of the negative 1 over t. So this means that the creep rate increases exponentially with temperature. Okay. So, and that also means that the stress goes down, because if the strain is going to increase, it takes less stress to to strain it. So the amount of stress needed is much lower at higher temperatures than it is at lower temperatures. Okay, so that's what this equation shows. Very similar as what we've seen in the past. Okay, so this is the way that we predict creep using tables for different types of materials. So this basically has the initial, secondary, and final. And we have our prediction of creep, rupture, lifetime. So this is for iron. We have a known temperature of 800 degrees C, and we're stressing this material. So it's a high temperature, 800 degrees C, and we're stressing it at 20,000 psi. So the time to rupture is T sub r. T sub r is located on the x-axis, and the stress is located on the y-axis. Okay. So let's put our givens down here. So we are given an S590 iron. And we are given that the time to rupture is predicted by the x-axis here. That x-axis has the equation temperature times 20 plus the log of the time to rupture equals L. Okay, so L are the numbers on the x-axis, and those numbers can be converted to temperature and time. Okay. We're also given that the temperature is 800 degrees C, and that the stress being applied is a constant stress. That's what creep means, 20,000 psi. Okay. And then we're going to do, I'm going to add another piece. I'm going to have a second temperature. What happened if we drop the temperature to 750 degrees C and we applied the same sigma 1? Okay. So what would be your estimate? Cooler temperature, applying a stress, the material should not rupture, should take a lot longer to rupture than it would at higher temperatures, right? Exponentially higher. So let's compare that. Okay. So we're given those. How do we solve this first scenario? 800 degrees, 20,000 psi. So I'll put the solution here. Okay, 20,000 psi. I have to look that up on my graph. If you look it up here, this side of the y-axis, the right side is in psi, the left side is in megapascals. So we go here, this is a log scale. It's because of the log in the equation. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Just remember the log scale. We're going to use these a lot in phase diagrams, so remember log scales. It goes by tens, so the scale before that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you count by tens, 20, 30, up that way. So 20, where would that be? 10, 20 would be right here. Go across till I hit my line. I drop down, and I convert my 20,000 psi into an L value. L value is the x-axis, and I'm getting 24. It says it's times 10 to the 3, so it's 24,000. And it's in, the units are given right here. It's in Kelvin and hours. Okay. So if we look at our things, we need to do some conversions, right? We don't want 800 degrees C, we want Kelvin, so that would be 800 plus 273 would be 1073 Kelvin. And then for later, we want to calculate this one. It would be 1023 Kelvin for our second temperature. So let's do that. And then the answer, we're obviously solving for time to rupture, it's going to be in hours, not seconds like our diffusion calculations were. Okay, so we take our value, 24,000 is our L value, and we already mentioned right up here that L equals temperature, which is 1073 Kelvin, times 20 plus the log of our rupture time. Okay, so we solve that. I get time to rupture equals 233 hours. This is at 800 degrees C. So 233 hours is, 240 hours. This is pretty much 10 days. So at high temperatures, with a lot of stress, this iron would rupture under constant stress after 10 days. Okay. Well, what happens if we drop the temperature just 50 degrees? We're going from 800 to 750. Again, it's the exponential equation. We could use the exponential equation if we had the activation energy for creep and gas constant, all those things. But that's why we have the table. The table already gives us that information. It has the trends that we see. Okay, so all I did was change the temperature to 1023. It's the same stress, right? So I haven't changed here, therefore my L is still the same. So the temperature is not dependent on this graph. It comes out of the equation, the T 20 times plus the log of TR. So we put in our new temperature, 20 plus the log of TR, still equals 24,000. I didn't change the stress. I recalculate, I get a TR of 2,890 hours, which is, this is at 750 degrees C. How long is this? This is about 120 days. So there's our exponential, right? I decrease the temperature only 50 degrees, and I increase the length of time this material is stable for 12 times. 50 degree decrease, 12 times longer. Okay. All right. So that'll end this lecture. Again, you need to watch this by before midnight, so 11:59 on Friday. And you need to follow the instructions I gave if you want to get any extra credit for this lecture, and those were given to you inside of the lecture itself. All right, I'll see you guys.